Okay, our next session will be about using vector search for clinical decision making, which sounds like a very exciting topic. And I want to welcome our two speakers, Erika Lesyshyn and Max Irwin. Erika works as a distinguished software engineer at EBSCO, and Max Irwin is a former colleague of mine, used to be a managing consultant at OSC, is co-author of AI-powered search, and now he builds AI-powered products at Max.io. And without any further ado, I want to hand over to our two speakers.
Thank you. Thank you for the introduction. As you heard, I'm a distinguished software engineer at EBSCO Information Services, and I'm here with Max Irwin, who is the founder of Max.io. And today we're going to talk about our journey to deploy vector search to production. So I'm going to start out with an overview of our products that are powered by our search ecosystem. I will then transition into the problem that we've been trying to solve for the past several years. I'll talk about our failures along the way and the solution that we ended up implementing. And then finally, I'll wrap up with an overview of our next steps on our roadmap. When many people think of EBSCO, they think of our academic and research products, but we're actually one of the leading providers of evidence-based content for point-of-care practitioners. DynaMed is one of our flagship products. It's really geared towards physicians in a fast-paced environment. You can imagine an ER doctor who needs to quickly diagnose and treat patients. DynaMedX builds upon this but contains additional in-depth drug information. DynaMed Decisions creates a bridge between patients and physicians to create shared decision-making to improve patient outcomes. And finally, Dynamic Health is really geared towards nursing professionals. All of these products are powered by our search ecosystem, which is composed of four main areas. First is our search prep. This is where content that's written by our editors is consumed and transformed into something we can work with. We then go through an elaborate enrichment process, which makes this content more discoverable. And finally, it ends up into our search index, which is now available in our search runtime environment. This is composed of two applications that work together. Query intelligence is aimed to understand the intent of the query and crafts runtime-specific search strategies that are executed by the medical search platform. We also have two types of feedback areas. First is our expert feedback. This is where we engage with our subject matter experts. They can create judgment lists, they can curate our knowledge graph, and they can also participate in surveys and experiments. And finally, we incorporate user feedback into the system to improve the quality of search. Now, at the heart of this ecosystem is our medical knowledge graph. We currently have two knowledge graphs in play. Our original knowledge graph is UMLS-centric. It doesn't contain all of the public vocabs, but it contains a subset that's specific to our domain. But it's quite large. There's over 355,000 concepts, 1.4 million terms, and you can imagine millions of relationships. It's quite a lot to curate. So we are also in the process of deploying a content-centric knowledge graph specific for one product. Now, the concepts are also derived from UMLS, but they are specific to the content itself. We then create a custom hierarchy that better aligns with our content versus what UMLS has. There's around 68,000 concepts in this version of the graph with 430,000 terms and just under 1 million relationships. I'm in the process of the next couple weeks deploying that. And going forward, we'll be moving more towards content-centric knowledge graphs. So how are users interacting with our system? What you see here is the way that we classify queries that come into our system. In this case, for DynaMed, I've shown 3 types of queries that we see. First is what's represented in green. These are simple queries. In this case, COPD is associated with a single concept, but that doesn't mean that it's associated with just the number of terms. For example, query nerve paralysis is also considered a simple query because those terms correlate to a single concept within our graph. And you can see here that the majority of our users are performing simple searches. Next, you have specific queries. This represents 2 to 3 concepts. And then finally, complex. This is where you start to see 4, 5, 7, 10 concepts coming into the system. This bucket of complex is really where we have underperformed in terms of quality. And really, the problem that we've been trying to solve over the past several years is focused on this complex bucket. You can see in dynamic health a similar pattern. The majority of queries are simple and specific, and we do very well in that space, but we really underperform in the complex bucket. Specifically, you can see that many times we have no hits returned, or we don't have enough recall. We know from our subject matter experts that there's additional content that we're not surfacing to our users. So here is a timeline of all the ways that we've essentially attempted to solve this problem and all the ways that we have failed. And I should mention the team size has changed over the years. I've been at the company now for 6 years, and different engineers have tried tackling different pieces of it. So I'm going to briefly touch on each of these areas. Our first attempt back in 2019 and 2020 was to simply just improve our Elasticsearch tuning. For us, it's really been a struggle to balance precision and recall. We have expert users, and they don't want a very long tail in their search results. They want to make sure that they're getting the best results returned, and we just don't have the ability to return a massive amount. But being that strict, we end up having a reduction in the number of results returned. You can see for this query, diagnostic techniques for lateral ankle sprain, that we're only returning 2 hits, and we know that there's actually far more content available. And this is a result of very strict precision, which is essentially an and joining all of our medical concepts together. Now, if you do the reverse, you get far too much recall. You can see that same query now can produce over 5,000 hits. Now, we did apply some minimum should match to reduce some of that recall. And that was something that held us over for a while. It gave us the space to breathe, to satisfy some of those queries while we looked for more sophisticated solutions. And so you can see here, we quickly decided that we couldn't simply go down the tuning route anymore. We then attempted to identify out of these complex queries which portions are most critical. And so what you can see here in this graphic is we attempted to identify, after we've broken down the query, which portions can be used as matching criteria and which can be used as ranking criteria. We tried supervised learning, unsupervised learning. We tried utilizing additional attributes from the public vocabularies, but we really failed miserably in this space as well. And part of the reason for our failure is it's hard for us to even verbalize what is most critical. You could talk to several different experts, and they might have different opinions. So it was a great idea, but we just could not get this to work. And so this was also eliminated as a solution. It was around this time that vector search started picking up more momentum, and so we decided to do our first POC. This graphic outlines the setup of our POC. You can see here on the left-hand side our ingestion pathway. We have a document coming in. We're utilizing a model to generate doc vectors, and then storing that in our index. And then, of course, on the search side, when users query, we're then taking that query, we're consulting a model to convert that into a query vector, and then also consulting the same index. But what's really key here is that we recognize that we only wanted to do this for a subset of queries. As I mentioned before, we're providing this classification for all queries that come into the system. And so our simple and specific queries continue to use Elasticsearch, but for this particular POC, our complex went the vector route. This is the results from our first POC. And essentially, what we ended up doing was we ran a blind survey just with the internal engineers of the team. And we evaluated user queries, and we had a random side-by-side comparison of the way search worked today and the way it would work utilizing this POC. This area in silver, I hope you can see it, shows that there was a preference towards the vector search, but we have this really large bucket of both bad, and then we have a significant amount of portion that still favored the old search. So we recognized that this was viable, but we knew that we needed to do tuning. And like any of you guys that have been doing this for many years, it's easy to create a search engine that doesn't necessarily produce high quality. And we found out the hard way it was easy to produce vector search that really doesn't produce high quality. So we actually went down quite a bit of a rabbit hole where we decided that the next steps was that in order for us to improve quality, we needed to reevaluate the models we were using as well as tuning. But as I mentioned, this was quite a bit of a rabbit hole. So first, we attempted to find a pre-trained model and played around with that. But we realized later that those models were word embeddings and not sentence embeddings. We then tried to use these models with the sentence transformer class, but they were not fine-tuned for sentence similarity, so the output just got worse. We went further down the rabbit hole and tried to add our vocabulary to pre-trained models using the expert architecture, but again, it made it worse. At this point, I put the brakes on this and said, we as a team need to take a step back and reevaluate the way that we're approaching this problem. So what we tried to do is evaluate all the different variables that need to be considered in order to produce a high-quality vector search solution. We focused quite a bit of our time on the model selection and tuning, but we neglected to spend enough time on the way that we were splitting documents as well as the technology that we're utilizing. When we first started our POC, we were using Elasticsearch 7.8, and we chose that because it's a familiar technology for us. However, the cosine similarity was not available in AWS managed services, which meant that we would have to spin up an EC2 container, deploy it, we would have to manage this additional cluster. And additionally, the performance wasn't that great because it was a brute force similarity approach. So we knew that when we embarked on our second POC that we would eliminate this immediately. That left us with AWS OpenSearch and Quadrant as two candidates to consider. The pros of OpenSearch was that it was available in AWS managed services, which is great. There's dashboards, there's visibility in what's going on. But it had recently been forked from Elasticsearch, and that divergence created a little bit of uncertainty in the future roadmap. We also weren't sure about the quality and the performance because we didn't do enough analysis on it. We did know, however, that Quadrant would work. We recognized that it would support our use cases. Unfortunately, it would require us, again, to have two different clusters to manage. But we could quickly eliminate this as a variable from the quality problem space and just move forward with the project. So we selected Quadrant. Additionally, we had to reevaluate the way we were splitting documents. One of the pitfalls of our initial POC is we took the entire document and kind of just shoved it in there and looked at what happened. We got a little bit better, a little smarter. We started getting smaller, maybe like a couple chunks of sections. But even doing a single section, they're so large that the input of the model was actually truncating a portion of the data, and we didn't even realize it. So let's take a look at how we're splitting documents now. In DynaMed, we have very long documents. We have 4,500. They are split into around 240,000 sections, And then they're further split down to 400,000 vectors. When I look back on our journey, we would have never have realized how much we needed to break down that content. In dynamic health, we have shorter documents that are only split into around 50,000 sections and then further divided into 64,000 vectors. Now, our document splitting is pretty basic today. Sometimes we actually split mid-word. So we know that we can improve the quality by improving our splitting mechanism. Another issue that we face is we have a massive amount of fragmented text in our content. You can see here that we have heavy bullets. And so we recognize that if we utilize summarization, that we can probably get a better portion of text before we vectorize it. And it'll allow us to create a one-to-one relationship between a section and a vector instead of this explosion. We also recognize that we needed to do more work on a model. So that's where we reached out to Max to help us. So I'm going to hand it over to him, and he's going to talk about that.
Thanks, Erica. While I leave this title up here that really needs to sink in, I'm going to thank you again. I've really loved working on this project. EBSCO is awesome. Erica's awesome. The team is awesome. If you're interested in evidence-based medicine search, talk to Erica. It's a really, really cool domain. So this title is really, really important because most people, when they start working on vector search, they kind of just look at what the blog posts and toy examples are out there and what models people are using. So it's really hard to understand which model you should use. And that's one of the first questions that people ask me is like, which model should I use for my vector search? It's a surprisingly difficult question to answer. So I'll just very quickly talk about one important thing. So anything that you put into a model that's off the shelf is likely to be what's known as zero shot. So that means that the model has never seen it before. So when models have never seen anything before, that means it's not likely to really understand what it is. So sometimes it can get lucky, and maybe it's seen something similar, but usually not. Because most of the models that you see out there that are off the shelf from Hugging Face were pulled from like general domain type stuff. So if you want to really choose a model, you have to look at the content that the model was trained on. So that means tracing back, going up, looking the model up in Hugging Face, and seeing what the actual training data is, and understanding the alignment between the source content for the pre-trained model, not the sentence transformer model, but the pre-trained model. Does it align with the content that you're likely to be giving it? So there are two steps in using a model. First is you need a base model that's trained on the content that aligns with your domain. So in this case, PubMed BERT is a pre-trained model produced by Microsoft, and Microsoft made this model just on PubMed central content. There's no Stack Overflow or Wikipedia or anything in there. It's just PubMed. So this is evidence-based medicine. So there's a very, very important domain alignment there because a lot of the content on DynaMed and Dynamic Health are based on research that's available in PubMed. So you're going to see a lot of the concepts, the vocabulary, general studies that are done. So this is how they train their model. So they took PubMed Central, which is a large in-domain corpus, and then they did, they trained the same model as like BERT, like BERT-based uncased, but instead they use this source content. So the source content is PubMed, so now you have PubMed BERT. And they wrote a paper on this. The paper is linked below in very, very small text up on the screen, but we'll share that, anybody who wants to know what that link is. So that doesn't do everything because that's just a BERT model, so that's trained on masked language modeling, next sentence prediction. We don't want that. We want a bioencoder, a sentence transformer model. So we didn't have at the time a specific training set for this model, but interestingly, the MS Marco data set, while not in domain, is an excellent source of similarity data. So one of the surprising things is that when you use a data set like MS Marco, which is really, really big, provides millions of examples on similarity, the source base model melds really well in understanding what similarity is, but also retains its domain context. And that's really, really important. We didn't actually train this model. This model is available on Hugging Face, and it was trained as part of a study to find misrepresentation in facts in health news, right? So they, a gentleman named Pritam Dekka, he did a study with a bunch of other authors, and in his study, when you look at these scores, which are really hard to see, but up here, SPubMedBERT is the model that was trained. This is a sentence transformer model with this base and with MS Marco trained with a couple hyperparameters that are available on the model card on Hugging Face. The scores here are like phenomenal. Like when you look at the other things comparatively, this is a really, really good candidate. Now there's still a lot of zero shot stuff because we are using an off-the-shelf model. It hasn't been trained on DynaMed or dynamic health content or relevance yet, but that's the next step. So when we get to the point where we're actually going to train this model, once we get past like the feedback step and understanding how users are responding to this, then tuning this model beyond MS Marco is going to boost the quality even higher for vector search. So there's two really, really important parts of this of the technology when you want to bring in vector search, kind of sideloading it in to your search platform if you're on Elastic or Solr and you've never done this before. So you have the model requirements, understanding that, and then you also have latency and speed requirements. Inference is very expensive and it takes a long time, so bringing that in, your SLA might get blown out of the water for response times and things like that if you're passing every single query through a model. So this is where my product comes in, which is called Mighty Inference Server. My company is max.io, but it's a product that's very fast. It's written in Rust, and you just give it a model, it converts it, and it deploys it so it's really, really fast, and you don't have to bring in a huge Python stack. The other important thing that I should note is that when you have your own separate inference service, if you were to deploy vector inference in your search engine, right? If you use like a language pipeline as part of your search engine like Elastic, or if you load an Onyx model into Solr, your search engine CPU is going to fight with the inference engine. You really need a separate service to do this. So you're not conflicting, you don't have conflicting priorities on the CPU. So for the requirements that we had, we chose a 16-core server on AWS. DynaMed and Dynamic Health are in AWS. This one machine, well, we have several because of development and production. The one machine is responsible for both ingestion and querying. You could split them out. You could have a bigger one for ingestion. You could have one separate for querying, a smaller one for querying. Maybe that'll happen at some point, but right now it's just easier to have one. Because the timelines of when content gets ingested versus when people are searching, it's like night and day. So there was not really a conflict there. There's also a custom reverse proxy that I built for EBSCO, where it's a single endpoint, and we'll have 16 different cores of Mighty hosted on this one machine, and this one endpoint will handle all requests, and it'll fan it out to all of the cores. So you get really, really high concurrency and very, very fast speed. So the latency on queries, it's about 30 to 50 milliseconds for this model, and I want to be specific there. The model dictates the latency. Bigger models, smaller models will change how long it takes to get vectors back. So for queries, it's about 30 to 50 milliseconds. For content, it's about 200 to 500 milliseconds. Depends on the number of tokens. And then the high throughput is because we're hosting 16 parallel Mighty cores, how many things you can pass into the server all at once. So we could re-ingest and everything in less than 6 hours, which is enough for overnight. We don't do a full re-ingestion every night. Very rarely do we have to do that, but it can handle that if we need to do it in a pinch. And just the cost of a single server, it's not much. So the complexity involved in having scaling, auto-scaling, and standing up, standing stuff down wasn't really worth it at this point, but maybe we'll get to there. And also, when there's no content being ingested, usually during the day, there's very little content coming through. up to 500 queries per second, which is like crazy fast. So this one machine fits the profile. So this, coupled with the in-domain model, is really important parts of vector search. And with that, I'm going to pass it back to Erica.
Thank you. Okay, so we talked about the different components that we reevaluated to improve the quality of vector search. And let's take a look at the results now in production. So for this particular query, what antibiotic is most appropriate for preseptal cellulitis? You can see that before we had no hits, and now we have some good results coming back. You can see here that the number of hits is capped at 10. So we are still doing some trimming, but it's nice that we have a balance here. Additionally, you can see on production today in dynamic health, cleaning and sterilization of reusable feeding equipment used to return no hits. And again, now we have a good mix. This has been very well received by our internal evaluators as well as our customers. So let's talk a little bit about how we evaluated the quality. As I mentioned in our initial POC, we did an internal review of the search engineers, but as we got something more mature, we engaged more closely with our subject matter experts. We have an in-house tool that allows us to show them two different sets of results. You can see in this screenshot, one on the left and one on the right. And the user is asked to pick whether they prefer the left, the right, or if both are good or both are bad. And it's random and it's blind, so they don't know which is which. So we had 3 subject matter experts, all physicians, and they rated the same set of queries. And you can see here that there was a high consensus among their evaluations, with a good amount preferring the vector implementation. You can still see here that we have some in the both bad category. So that's an area of improvement that we can work on. But we also recognize that these queries are coming from our logs, and they may actually not have appropriate content associated with it. And so it does require some evaluation to see if they are, in fact, appropriate queries that we can tune. So I'm going to talk a little bit about how we integrated this into our ecosystem. What you're seeing right here is our nightly refresh. We essentially rebuild our graph nightly, and we notify Query Intelligence to refresh its caches of the graph, and then we re-ingest all of the content, because we want to ensure that that all of the changes to our knowledge graph are recognized and semantically enriched nightly. So we recognize that the work that we would do would fall within this re-ingestion process. So when a piece of content is published, we first go out and we fetch it from S3, and we continue to do our regular enrichment by consulting our knowledge graph and additional metadata decorating. But now we're also calling Mighty, and we're generating those vectors. We're also indexing it in our Elasticsearch, but we're also passing it off to Quadrant as well, and then notifying the callers upstream of the outcome of this event. And what you're seeing here is a lot of the work that we ended up tuning and focusing a lot on was ensuring that this was done within a certain time frame. Because we're processing all of the content overnight, we wanted to make sure that we stuck with that window. And so what we're doing is we're breaking the content down into those vectors, and then we're doing parallel processing to consume, to generate vectors. Now, this is a very expensive operation, as Max had indicated, so we are storing that intermediate result in S3 prior to indexing it in Quadrant, and this allows us to quickly rebuild indexes. Additionally, when we consume content nightly, we skip the expensive operations if the content hasn't been updated recently. We also spent quite a bit of time working on our dashboarding. And you can see here by these metrics that we needed to take special care to ensure that the way that we were implementing it was correct. An AN is a single document that can be exploded into sections, which can be further exploded into vectors. And we also want to make sure that we're measuring the time associated with it. Now at search runtime, a query comes into the system. That query is passed off to query intelligence, which is really aimed at understanding the intent. So the first thing we do is we segment that query. If we recognize that the query is in fact complex, we not only consult our knowledge graph, but we also go ahead and generate vectors for that query. We also perform some query expansion, some filtering, and then we pass this runtime specific recommendation back to the medical search platform. And then it makes a decision on whether it should consult Elasticsearch or Quadrant to fulfill the content need. Now let's take a look at how this has been received in production. So what you're seeing here are the key performance indicators. On the right here, you can see our regular search. This is our simple and specific. The green represents customers that we have with a high degree of confidence that they are satisfied. They entered their query, they found their content, and they got back to working with patients. We also have a bucket of moderately satisfied, around 13% fall into this category. These users have perhaps changed their query. They've done a little bit more work to find their answer. But again, we have a degree of confidence that they were happy and they've left the system getting what they needed. And then we still have a chunk of unsatisfied that we'll continue to tune. Now let's take a look at how vector search is doing so far in production. You can see that we have a big chunk that still aren't satisfied. And as I mentioned, part of that is we may not have content to match their information needs. But it also means that we need to do some tuning as well. But we do have a significant amount of users that are highly satisfied, and prior to this, it was very low. Oftentimes when a user enters a query and gets no results back, it may actually give less confidence in the quality of our search. So the fact that we're giving more recall and we're getting closer to their answer has definitely resonated with our users. So let's talk a little bit about lessons learned. I think one of the biggest challenges we faced was balancing when we should fail fast or when we should slow down and try to absorb more information. And as I mentioned earlier, we went down some paths where we went down a rabbit hole. And that rabbit hole, maybe we were there for 6 months, 9 months, and it's very hard at times to convince people to cut and reevaluate and take a step back. But other times we felt that we probably didn't spend enough time evaluating different variables to our problem. So my advice would be, if you are going to go out and implement vector search, would be to make sure that you allocate enough time and consider all of the variables. As I mentioned before, it's actually pretty easy to create vector search that isn't that great. It's a lot harder for a domain-specific area to get better quality. Additionally, we've recognized that maintaining 2 different search engines is a lot of overhead and adds quite a bit of complexity. And so we're already beginning the process of starting to merge them together, not only to support those different use cases, but additionally to blend them together to combine vector and concept search. So our next steps is to certainly continue to review how it's being received in the system. We're going to be tuning the models. And then, as I mentioned, we are going to be combining them together. And that is it. Are there any questions?
Thank you very much. There's already a question here from the audience. And while I go up there, maybe I pass on one question from the chat. So Chris for Leska asks, what's your team size for search? Not just engineers. So how many folks do I need to implement vector search?
Okay, well, that's interesting. If I go back, let me see if I can find this slide here. So over the years, the team size has changed. Right now, we have about 4 engineers. There are other times where we had search engineers, we had ML AI engineers. We had a mixture of probably around 8. For us, it actually feels that if we're smaller and we're all specialized, we can actually get more done. But I think our current makeup, we don't have any one individual that knows everything. We all complement each other. But I think, obviously for different organizations, it's different.
Awesome. Heartbreaking to see Elastic 7.8 up there being rejected for vector search. So I hope that it's in the running for maybe testing for your combined search. But my questions are, I have 2 questions for Max. One would be, do you do any caching layer? And 2, do you do any model weight quantization or activation quantization to take advantage of hardware acceleration on inference time?
No, and for this model, no, but it can support quantization. Quantization is really tricky, and there are a lot of different models out there that use a lot of speed increasing techniques. So quantization is one, sparsification is another. Sometimes there are drawbacks, like specifically with sparsification, you have to pad every result in a lot of the models. So not all of them, but in a lot of the models you have to pad results. So a lot of the models just get really slow at query time because you're padding to the maximum input length anyway. But there are a lot of advancements being made. I'm trying to keep up with everything that's happening. It's kind of crazy out there. But the caching is an interesting question. I debated that. The answer is no, because specifically, for EBSCO, these are tail queries, right? These are complex queries. You don't see them a lot, so there's no point in caching them. But for head queries, you'll find the simple and the specific queries. I don't really think vector search is a great solution standalone for that. You have 1, 2 concepts. BM25 is going to do way better. So that's the other thing. Don't use vector search if you'll have 1, 2 search terms. BM25 is the way to go with that. So caching with inference, I don't really see a huge need if you're doing it right.
Okay, thank you. One more question maybe related to platform choices from the chat. Dimitri Khan asks more or less about the exclusion of the many other vector databases available a priori. So you went to 3 choices straight away. So what was the reason? Why were they excluded? Or was there any reason at all?
Yeah, great question. So as you can see, we've been trying to work through this for quite some time. So we recognized that we didn't have a massive amount of time to evaluate all these different options. We ended up going with what we knew we could quickly eliminate that would be viable. But now we're in a point where we can start reevaluating and continuing to explore. But like anything, once you start, it's a continuous improvement process.
Thank you.
Could you kind of comment on some of the variables you feel you would wish you would have spent more time on, or maybe a little more on those lessons learned?
Absolutely. Let me see if I can pull up. We spent way too much time on the model selection and tuning, and really didn't spend enough time on the document splitting. And I think when I've attended these conferences before, we didn't really recognize that that was such a key component. So I think the big takeaway was, first, I think we had a lot of different engineers try different things, and we had the best success when we brought everyone together and brainstormed on the problem. So if you don't have a siloed approach, I think that's important. But in our case, definitely document splitting was huge, a huge impact for us. And obviously, incorporating help from Max, putting the brakes on this and saying, let's reevaluate this model tuning selection rabbit hole, and really cutting bait and then reevaluating and started fresh.
Next question here.
So going further into that document splitting, I think when you talked about it, you mentioned that the challenge of where to split, and sometimes you're just doing it arbitrarily. I was curious, why not leverage the structure of the document? Because the document itself is imparting a lot of information. Is there something wrong with the medium that doesn't allow you to pull out the features?
Yeah, let me pull up that slide if I can find it here. Okay, so our documents are structured, so we do follow the hierarchy. We actually break them down into sections for our Elasticsearch index, but even those sections are massive, and so we need to continue to break those down further. But as I mentioned, actually in this slide here, you can see we have 240,000 sections, but 400,000 vectors. So you can imagine, that breakdown continuing to create more and more vectors. We would like to move more towards a one-to-one relationship where we're aligned not only with the structure of the document and the sections, but also the vectors. We will only get to that point once we start actually summarizing that content before creating a vector out of it.
Okay, one more from the online audience. Have you considered combining vectors and BM25 hybrid search for these complex queries?
Yes, so just in the weeks prior to coming to this conference, we have what we consider dedicated innovation cycles. So for every 10 weeks of work, we have 2 to 3 weeks where we can work on anything. And I did explore that. I explored it with OpenSearch. It looks very promising. But as I mentioned before, we'll be evaluating many different engines to see what meets it. But it does feel like we are absolutely moving in that direction. It's just getting other work items off our plate before we dedicate and shift gears. But it does feel like it's the best of both worlds.
Hey, Erica, I wanted to first congratulate you or give you kudos for sharing the lessons you've learned on this journey and being transparent about that, because oftentimes at conferences we look at wins, but we don't necessarily look at where we failed or where we've learned. So first, just kudos on that. My question is, when I was listening to this presentation, I saw two ways in which this is evaluated. So it sounds like you had internal subject matter experts evaluate, and then I saw that with your end users, there was some kind of explicit satisfaction or feedback. Have you considered engagement-based measures? And if not, or if you have evaluated them, do they align with what you're seeing in terms of the subject matter evaluation? Why not jump to looking at engagement as a way of evaluating the end user quality?
Yeah, so I hope I understand your question. But essentially what we do is we start out with an internal evaluation. We consult with our subject matter experts. We typically engage with external experts. So we'll work directly with board members, experts in the field, but individuals that we've asked to compare us to our competitors. We've also had external companies go out and evaluate us as well. And then in addition, looking at user behavior. And oftentimes you can see that there might be a disconnect between what a user says meets their query versus a subject matter expert. So we actually have a system that shows us when there's a disconnect between a judgment list that's been generated by an internal expert versus a judgment list that's been generated by user behavior. I'm not sure if I addressed your question.
I'm mostly asking, at the end of the day, you have users that use the product in the clinical setting, and they'll do a search, and some of them will search and not see what's relevant and not engage. And some of them will engage with it, will click on the document. So I guess I'm asking, why not use the engagement, the implicit engagement data as the main evaluation source for whether or not the search is working well?
Yes, so we do. We create judgment lists from subject matter experts, but also from user engagement in the system. So we have two types of judgment lists that we interact with.
Hi. My question is, do you specifically ask your users for like search quality in terms of maybe like a thumbs up or like a rating of some sort?
Yes, we do. So on the products, there's been initiatives to have free-form feedback that they can input in the system, but also the easy thumbs up, thumbs down as well.
Okay, we take one more question from the audience. I think Doug had one and one from the chat.
I was curious if you used any query feedback mechanisms, like seeing what people interact with. So short queries sometimes work better if you know that if I search for shoe, I click these 3 things, and if you use vectors from those documents to then search the index.
Not for this project, no, but that's really interesting.
Okay, and finally, a question from Theo Harrison, and I apologize to all the people whose question we cannot answer here. You displayed a use case where you still feel you may not be returning enough results. Can you talk a bit more about the pros and cons of returning more or less results as you evaluated the right thresholds for vector retrieval?
Yeah, that's a great question, and it's very hard for us because you might have some feedback that people don't want to see anything that's relevant but not an exact match to what they're searching for. And then you also have feedback where perhaps they want to see more recall. So it's been very difficult for us to find that happy medium. For now, we're doing a brute force cutting. We're essentially saying, in the case of vector search, we're maximizing the maximum number of, we're capping the maximum number of vectors returned, but we need a more sophisticated way to determine where that cutoff should be. Because as we know, it can continue to just return everything with a lower scoring.
Thank you very much for probably the first case study on vector search at Haystack, right? Maybe? Thank you very much.
Thank you.